Okay, so we have made this all important definition of the derivative of a function, which is defined as an open set. And now this is a multivariable situation. So your open set is in some Rm, and the target is of this function is Rn. So the reason why we have an open set is because if I am calculating the limit of whatever quantity around a point, at a point, then there is wiggle room around that point. So I can approach that point from all directions. Okay, so what does it mean to say that a function is differentiable? Well, I have written the definition. The key thing to remember here is that the derivative of a function. Okay, so continue, the definition continue. The point is that the derivative of a function is not a number, but the derivative is a linear map. A linear map from the same space in which where the set U is sitting to the target vector space. So this linear map is also from Rm to Rn with the same M and N as a power. And how do we connect it with our one variable situation? If the derivative of a function of one real variable that takes a real value at a certain point is a number, let's say constant C, then we really think of it that constant C as a linear map taking X to C times X. Okay. So every real number defines a linear map from R1 to R1. If we keep that in mind, then the one variable situation is really just generalized over here. Okay. Now coming to the definition itself, f is differentiable means there is a linear map T such that what happens if I calculate the difference between f of a plus h and f of a, then that difference minus the linear operator T applied to the vector h. That difference, when I divide it by the norm of h, that should go to 0 as h approaches 0. Okay, so there are a number of questions that come up immediately. The very first one is that this definition says if there is, it's about the existence of a linear map. So the question is, will there be multiple such linear maps? And the answer is no. So definition continued. So we call such a linear map T the derivative of f at a. And this the really needs to be justified, which we will, that's the first thing that we will do. So the derivative of f at a. So we can call this in many ways. So let's say denoted f prime of a or b of f at a. Okay, so this the needs to be justified. So let's do that. Let's do that as the very first thing. Okay, so sorry, before that. So the question is, look at the definition once again. Here I have taken norm at the top as well as norm at the bottom, in the numerator and denominator. The norm in the numerator is norm where?
In Rn.
It's in Rn. Whereas the norm in the denominator is in Rm. Okay. So the question is, does this definition depend on the norm? If I choose a different norm on Rm or Rn?
No.
Why does it not?
Because on finite dimensional vector spaces, all norms.
Right. So all norms are equivalent. See, all norms are equivalent and they give the same topology. But here it is not just a question of topology. I mean, we are calculating actual numbers here. So maybe a little bit more. So why does the fact that all norms in a finite dimensional vector space, they're all equivalent? Why does this show that? So what does it show with respect to this?
Because we have that limits. It shows that all limits have to go to the same values irrespective of the norm, because if we take let's say just mod x minus y, that is less than or in one norm, that is less than or equal to some constant times norm of x minus y for the other norm. And because of that bound, if one goes to zero, the other, if the greater one goes to zero, the other one has to go to zero as well. So,
right. So I hope that everybody understood what he just sketched. Correct. See, if I use a different norm, then for a specific value of h, if I calculate the numerator and if I calculate the denominator, if I use different norms, those values will actually be different for any specific, for a specific h. But as h approaches zero, first, as h approaching zero in one norm versus another norm doesn't really matter as long as the norms are equivalent, because you see, one norm is bounded by a constant multiple of the other norm, right? So if some real quantity goes to zero, then a constant times that real quantity is also going to go to zero. So if I'm using a different norm, then for a given epsilon, the delta that sufficed for one norm may not suffice for another norm. But the point is that because the norms are equivalent, if I have an old delta that worked for a given epsilon, the new delta that will work is just a constant multiple of the old delta. So in particular, the limit will stay the same for the same t, right? So, okay, so needs to be justified, and we'll just say needs to be justified. So below, but remark, if a linear map T is okay, so that sentence if the above limit is zero for a certain t with respect to some norm on Rm, respectively Rn, then is zero with respect to any other norm on Rm because all norms on Rm, respectively Rn, are equivalent. Remember, norms being equivalent is a very strong condition. It says that one norm is within constant multiples, both above and below, with respect, compared to the other norm. So, okay, but first, so this is out of the way. Let us show that the derivative is unique. So claim derivative, if it exists, is unique. So that means let's set up the terminology. So what it means is that under the given condition, that is under this situation, I have a linear map T such that this limit is 0, but I also have another linear map. So what shall we call it? S maybe. Which is to say, if in the above situation, limit as h approaches 0. So this whole thing I have to write, right? F of a plus h minus f of a minus t of h. In the beginning, I will remember to write this t of h, but later on I may simply forget it, okay? But really there is no possibility of confusion because there is no way to multiply something called t with something called h. T is a function and h is a vector. So divided by h equal to 0, but it is also equal to limit as h approaches 0 of the same thing, but with a different minus, let's say, some s of h. Then what must happen? Come on.
S of h is equal to T of.
Yeah. So in fact, then T is equal to S. And what does this equality mean? It's an equality of linear functions. It's the equality of functions in particular. What does equality of functions mean?
They are equal at every point they are acting. I mean, in Rm.
Correct, exactly. Which is to say T of
We
V.
can also say in terms of basis. I mean, they agree on a basis.
Right, but we don't need to do that. I mean, so in this case, so just going by definitions, equality of functions means for every input. So for all V in R M. So this is what we want to do. Well, so what we will do is we'll take their difference. So let's call their difference to be something. So proof, let difference maybe, okay, R. R is equal to S minus T. So what I'm going to calculate is, let's do the calculation. So what is R on any, and let's use H as the letter. So what is R applied to H?
S of h minus T of.
S of H minus T of H. So I've dropped the parentheses. So you see, I want to now get the above things over there. So I'm going to do the following. So this is going to be f of a plus h minus f of a minus t of h. But of course, I have put this extra junk over here, right? So I will subtract from this f of a plus h minus f of a minus s of h. Correct? I mean, usual kinds of tricks. Now, what I'm going to do is I'm going to divide this by h. But of course, when I divide this by h, I have to take the norm. So everywhere. And this starts looking like, and I will separate it out. Right? Okay, good. So now I'm sort of in business because now I can start taking. But now here is the thing, you see. So the goal is I will show that the limit of the left-hand side is 0 as h approaches 0. Because, I mean, it sort of suggests I should do that, right? Because on the right-hand side, I have now recognized ratios whose limit as h approaches 0, I know something about. But still, if I take the limit of the right-hand side, Okay, so here is the thing. So let's put this. Now, can I put these norms individually? And no, the answer is
Sir, I will have to use triangle inequality.
right, exactly. So so in fact, let me not do this. Let me just. But the point is, you see, this is less than or equal to the sum of individual norms, right? Now this minus doesn't really matter. The minus I can put inside the parenthesis, correct? So f of a plus h minus f of a minus t of h divided by norm of h. Okay, so what's going on over here? Okay. And then plus f of a plus h minus f of a minus s of h. Is this okay? Just by triangle inequality. But you see, both the left hand side and the right hand side, they are positive things. Certainly non-negative things always, right? So I take the limit as h approaches 0. What do I get? Just look. Both the limits on the right hand side are 0. So there is a positive quantity that is going to 0. So a positive quantity that is less than or equal to that quantity is also going to go to 0, right? So limit as h approaches 0 of RH by h norms. Okay. So far, so good. But what is it that we want to show? So that's what we want to show, no? The difference that S and T are the same function. So R evaluated at every vector E is 0. What this is telling me is that the norm of RH divided by the norm of H, that quantity goes to 0 when I take small vectors H. I mean, that as I keep taking smaller and smaller vectors, the limit of this quantity is 0. But I would like to show that R evaluated at every vector is 0. So what can I do? You see, there is something over here, right? Some extra thing is required. This is allowing me to say something or the other in whatever epsilon, delta, etc. Only when the vectors H are small. But I want to see what happens to R of any vector.
I might be wrong, sir, but I think we need to define a notion of norm of a matrix. Am I right?
We will, but not here.
Hello?
There is no, right. So we will, but here it is not necessary. You see, the idea is I'm taking norms only of vectors here. The point is,
Hello, sir.
yes.
I think we can take h to be equal to lambda times v.
Okay. So this is one small idea, but a useful idea. In that, you see, this is a norm, and norm is homogeneous. So scalars come out. So yes, you can say, oh, I'm taking R of only small vectors, but I can take those vectors in any direction, right? So here is the thing. So first of all, so I want to show that R of V is 0, but I can take V to be only non-zero vectors because, R is a linear map. So of course, R of 0 is 0. So for any non-zero V, or let's not, okay, so maybe instead of saying fix any non-zero v. Now, and you can notice that, so here is the point, limit as lambda approaches 0 of lambda v is 0. So take h is equal to lambda times v. What is RH by h? RH by h. Of course, if I have to divide by h, I have to take norms here. So what is RH?
Lambda time.
Yeah, so here is the thing, no? So okay, so maybe worth writing this down. RH is equal to R of lambda h, lambda v, which is lambda times R of v. And why is that?
R is linear.
Right, okay. So I should really say lambda is in the real. R is a linear map. So, so plugging that in, and of course, norm of h is norm of lambda times v, but I know what norms work like. So this is lambda times norm of v. Of course, what I should do is not just write lambda times v, but put absolute value of lambda times v, correct? But in the same way, norm of RH is also going to be absolute value of lambda times norm of RV. Yes. Too many vertical lines, but I hope you see what's going on. It's very simple. So what is the upshot?
Lam-
Right. So, and let us say lambda is not 0. Because then I get to cancel it. So this really is the same thing as norm of RV divided by norm of V. So what does this mean? So this is really saying that limit as, you see, this limit as h approaches 0 of that ratio being equal to 0 is really telling me that I can approach h from any direction. I mean, h can approach 0 from any direction, because you can do this in terms of epsilon and delta. The point is, whenever the norm of h is less than delta, given any epsilon, whenever the norm of h is less than delta, the norm of RH is going to be less than epsilon. But this is true for any h satisfying that property. So in particular, it will be true when I take h to be lambda v. And I'm taking lambda to be small in order for the norm of h to be small. But you see, that ratio does not really depend on lambda at all. So what we are saying is that limit as h approaches 0 of this limit, which is supposed to be 0, but that really is the same thing as limit as h approaches 0 of this. But that's a constant. It doesn't depend on h at all. So what this is saying is that this is 0. But what this means is that the norm of RV is 0. Because remember, V was a non-zero vector. It has non-zero norm. But that means that, what does it mean that a norm of a vector is 0?
That vector is 0.
Right, only 0 vectors have 0 norm, right? Which is what we wanted to prove. Okay, so okay, I sort of drew this out quite a bit, but this is a very standard thing. And the idea is going to be useful in that, on the real line, when you took limits, in school, you were like always about, oh, left hand limit, right hand limit, etc. Okay, so here the same idea becomes that if the limit of a function exists as whatever x approaches some vector, in the multivariable situation. If the limit exists, it means that really your point can approach from all directions. That's exactly what we have utilized over here. Except in the situation here, it turned out to be a very simple situation because what we were calculating, only a linear operator was involved. So, okay. So it may seem like I have written a lot here, this proof, because I just wrote everything down, but this is a very easy and simple proof. I mean, in your mind, it should feel like a very simple, completely standard. Okay, any questions so far? All right, so let's draw a line under this. We have shown that the derivative is, when it exists, it is well defined. All right, so what are the... sorry, does somebody want to say something?
Yes, I was thinking, can we think of it as, if it's a sort of linear map, like then if the derivative at 0 is 0, then the derivative everywhere is 0. So like map on v divided by v is. So I mean, for if it was a real line,
Okay,
passing through the origin,
right,
and as the limit tends to 0, rv by v was 0.
right.
Then rb by since the derivative is constant, so then rb by v would be 0 everywhere, I think.
Okay, so I am not really sure what you are getting at over here. But you see, one thing is true, right? Which is that if the derivative is 0 at a certain point, it does not mean that the function is constant everywhere. The original function. So let's keep this in mind here. This function R as a linear function is really looking only is relevant. Okay, so this is coming out wrong. The point is we are looking this function R, I mean the function S, T, R, they all have to do only with the infinitesimal behavior of the original function only at A. So if you want to draw analogy with the one variable situation, which is always a good idea, okay, by the way, that whatever you're thinking about in the multivariable situation, if you specialize to one variable, it should be true, correct? What we are saying over here, this amounts to is that if I draw the tangent line at any given point, it will have a unique slope. You cannot have two different tangent lines. That's what this is saying.
Yes.
Because the linear operator in that case is just the 1 by 1 matrix given by the slope of that tangent line. And at different points, the function may have very different slopes, and they almost always will, unless the function is itself is linear. Okay, so this actually gives a very simple but easy exercise, which you really should do for yourself. Example: if f from Rm to Rn is a linear function, is a linear map, then I'm asking what's the derivative of a linear map. And if you think of one variable situation, what do you want to answer? The derivative of a linear map is what?
So constant.
Okay, but you see, again, you should sort of think of something that we have not yet come to. When you say that the derivative of a linear map is constant, what you really are saying is that you are regarding the derivative of this map as a function. You are calculating the derivative at every single point and seeing how that varies. Correct?
Yes.
Right. So far, we have not touched that issue at all. We have defined the derivative only at one point. Of course, if the derivative is defined at multiple points, and for nice functions it will be, then the derivative itself will be a function. From where to where? This is something that we will come to and discuss. All right. But right now, I'm just asking you some very simple question. Remember, the derivative of a function at a given point is a linear map. So which linear map is that? What's your guess? F is a linear map. Its derivative at any point is also going to be a linear map. Which linear map?
F itself.
F itself. Does this make sense in the one variable situation? Just think. F of x equals 3x. The derivative of this function at any value a is 3. But as a linear map, what is it? Let's use a different variable now. Let's take the variable h. The number 3, regarded as a function, is the map that takes any h to 3h, right? So as a function, it's the same as the earlier function. Okay. So this may look extremely weird if you think of this the way you are thinking of, the way you would think in the one variable situation. So this is a viewpoint change that you have to do here, that thinking of the derivative as a linear map. You have to fix that in your head. Okay. So see that this happens. How do I want you to see this? So immediately, and more generally, what will happen is that even for an affine map, the derivative is very easy to calculate. So what is an affine map? Similarly, for an affine map, in fact, we might as well discuss this. For an affine map, so where a vector v goes to what? So, okay, what is a linear map from
V
Rm?
plus something.
So what is a linear map from Rm to Rn? Where does a vector v go? So in fact, let's write this down. If f is a linear map, every linear map from Rm to Rn has what form? What form?
It's a linear combination of some particular vectors in Rn, where those particular vectors have to be a basis.
Okay, so you may be
But
right.
we
but
can
that's-
multiply it by the matrix. If
Okay, so you multiply this by a matrix, right? So, okay. V is equal to AV. For a, what will be the size of this matrix? It's a linear map from Rm to Rn. So what will be the size of the matrix?
N by M matrix.
N cross N.
And very shortly, you're going to need to answer the following question. If I give you a linear map, how will you build this matrix E? Okay. So if the answer is not immediate, then you should think about this. All right. So an affine map is going to be simply a map of the type AV plus some constant C. For or maybe in your linear algebra classes, you called it vector B for sub C in Rn. So what will be the answer over here? Similarly for calculate. So let's say G, calculate G prime for some. What will be the answer? Again, it will be calculate G prime of A. And what is the answer? G prime of A is equal to the map that takes V2, or let me say H2, capital A times H. This is straightforward from definitions, but it really is a good idea to do this. Okay, so let's get a move on here. So what are the immediate questions to answer? So immediate. Immediate issues to address. So one, think of the one variable situation. What were some key things about the derivative, foundational things about the derivative? That quality of that silence I don't particularly like. Okay, so what were some basic theorems about the derivative? So if f prime of A exists, then if a function is differentiable at A, then
Continuous searching.
is this a difficult theorem? Yeah, so this is not a difficult theorem. That means that your proof that you have in the one variable situation, you should be able to adapt it. Right? So we don't have much time, but I do want to do this then. But maybe something more interesting. What is a fundamental theorem about a differentiable function? It's really one of the bedrocks of real analysis.
The mean value theorems?
Yeah, so the mean value theorem. Correct. Okay, so maybe write that, but before that also.
Sir, the derivative of sum of function.
Right, exactly. So the calculus of derivatives, right? So here is the thing, chain rule. That's sort of the interesting one, right? And the product rule. Chain rule, maybe I'll say other rules. The thing though is that, does it really make sense to take product rule here? Can I add, so you see the functions are from Rm to Rn. What can I do with those functions? I can compose such functions. Of course, M to N and N to L, some such function, it can be composed. Can I add functions from Rm to Rn?
Yes, also dot products.
Well, okay. I can, right, okay. So I really cannot multiply vectors, right? In the sense of getting another vector. But okay, I can do the dot product. Yeah, I can do that. But it's really quite different from
Cross product or something.
Right. Now the cross product is a very special case, right? The cross product can be done only in
R3.
right. So that's a very special thing. Anyway, so you can think about it. But so you see, the fact that when I add functions, their derivatives also add, or when I scale a function by a constant, the derivative also gets scaled. That's really the linearity of the derivative operation. So you can think about it, but certainly the chain rule is a fundamental thing. And of course, mean value theorem is absolutely foundational. Where do we use mean value theorem? Some applications.
So increasing or decreasing nature of
Right,
function.
exactly. And if you want to say extreme values, if a function is differentiable at an extreme value, then what can you say about the derivative at an interior point? If you have a
So it
local,
has to be 0.
right? So we said in the beginning that whatever we did in the one variable situation, we would like to be able to do in the multivariable situation. So these are some of the basic theorems, and we want to do that. But so let me just say exercises. We will do this in class, but today we are not going to be able to get there. So you should do this, and you will find that for doing one of these, it will be a useful thing to try to calculate try to define the norm of a linear operator itself. It will be a desirable thing. So far, we did not need to do that. But one thing that I want to do is this is what I sort of want to end with. Matrix of f prime of A, of course, with respect to standard basis of Rm and R. So we come back to this question. How do I
So Taylor's
okay, so let me
This is the Jacobian, right?
forget the Jacobian. I'm just stuck. We will call this the Jacobian, but I'm asking a very, very basic question, which is, okay. Any linear map from Rm to Rn, any linear map from is not of the form, is given by the formula T of V equals AV for a uniquely decided and n by m matrix A. So I said we know that, we better know that. Okay, this is a very basic thing. And as a test, I'm going to ask you. How to find it.
We look at what the linear map does to the basis vectors for some basis.
Right.
And then the coefficients are the entries of the matrix.
Written in what way?
I mean, that.
So, okay, I take a basis vector. So here, so one thing I would just like to add, if I want to write down the matrix of a linear transformation, I have to have a basis in the source and the target space. Without that, there is no writing the matrix. So you see here, when you write A times V, it really is A, and the vector V is written as a column vector here. Okay. So, okay, so let's go with what you were saying. How do I write the matrix of A? You said that we'll take A, write down T, and calculate T of E1.
So T of E1 goes to the first column, what do you call it? The first column.
So let us say the T of E1 is going to be A1
into some E prime 1, the basis vectors of the other vector space.
Okay, so basis of R M is equal to E1 up to EM. Oops. Basis of R N. Now let's not go with primes, okay? So okay, so but this is bad because if I say F, all right, let's I mean I dislike this intensely, but E1 prime up to En prime. Then if T of E1 is going to be A1 E1 prime plus up to AN En prime and so on, then what is the matrix of T? How do these numbers A, how do these numbers A1 up to AN, where do they land? Then A is equal to
They form the first column.
A1, A2 up to AN. But you see now my notation is going to be bad, because if I then want to write T of E2 is equal to what, B1 E1 prime etc., then then I don't know at which letter to end with. So if this is the case, then I have to do double subscripts. Now, the moment you do double subscripts, you can get confused which one is rows and which one is columns. So let me here just stick with this. Let's say B1 E1 prime, Bn En prime, and then the second column will be B1 B2 up to Bn. And I simply have to say dot dot dot, whichever letter I end up with, right? Depending on what the value of okay, so A1 B1 okay, so how many columns is this matrix going to have? This matrix is going to have m columns, right? Okay, now there is absolutely no mystery about this, because what happens is that when I multiply, notice AE1 is equal to A1 B1 dot 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 A2 B2 dot 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 up to AN BN dot dot dot. I multiply this 1 0 0. What do I get? So reason is very simple. Answer for a very, and what is the reason? How do I multiply this matrix with the vector? And just carry it out the way you do it in school. And what happens? When I multiply the first row, A1, B1, and so on with this column, what happens? I just get, what is the first entry over here? Come on. That's just A1. And similarly, if I multiply the second row with that column, that gives me the second entry, which is A2. So this is the reason why, to write down the matrix of any linear operator, once I choose basis in the source and basis in the target, the recipe is very simple. Take your chosen basis vectors one by one, take the first basis vector, see where it goes, take the coefficients of that, write that as the first column of the matrix, and so on and so forth. Okay. In your linear algebra course, you should have seen this and it should have been ingrained in your mind. But if it was not, then this is a chance to do it again. It is very simple. And as an exercise, what you should do is you should put together the definition of the total of the derivative f prime a, write down its matrix by this recipe, and you will see that the matrix entries that come out are precisely the partial derivatives that we defined. Okay. So this is an exercise that we will do in class, but it is exactly the kind of thing that you have to do for yourself to see what is going on. It is very simple and transparent. Okay. The type of trick that we will do one little extra thing is exactly what we did over here in the first one. Since h is allowed to go to 0 from any direction, I am allowed to choose a particular direction. So in this case, what you will do is, instead of taking arbitrary vector v and h to be lambda v, what you will do is you will take h to be lambda times ei, going from the ei'th direction. Okay. And you will calculate the directional derivative in the ith direction. But f itself will have many components. So if I take the derivative of the jth component function in the ith direction, you will get the respective partial derivative. All right. So this is how the proof is going to be. Already I told you the idea. I will write down all of these proofs in class the next time. But really, if you want to understand, you should do all of these proofs on your own. Okay. So with that, let's stop for today.